Thank you, and I will now talk about an example of the execution model presented by Jeff Bowling a little bit earlier. We worked with the FAA for a couple of years on this project. Of course, the whole purpose of the FAA is to provide safety, and so that we have the confidence that we have today that you can get on a plane and fly somewhere equally as safely or even more safely than if you had driven there. And that is the goal. But the concern that the FAA, some aspects people in the FAA have had is, as we get more and more complex systems, and they were specific not to just software, but the systems, say the avionics system on an aircraft, for example, as we get more and more complex, is there going to be some point at which we can no longer say this system is safe? We can't certify it. And so they asked me to lead this project, and I'm thinking, well, I don't know if there's going to be an answer to that, but I suppose that's why we call it research. But we did come up with a good answer. In addition to that particular question, I want to point out that once you have determined a way to determine the safety given some complexity, we're also looking at similar problems across the DoD. For example, any particular quality attribute mentioned earlier that depends on, say, counting numbers of pieces is going to get more and more complex to try to figure out what the value of that is as you get more and more complex systems. So we believe our approach can help, and I'll show you why in a little bit. This is the execution model shown to us by Jeff. We have the applied research and development on the left with engagement in the field and transition activities on the right. And where it fits with the FAA project is as follows. We had this project called Measuring Complexity for the Purpose of Safety, System Safety Assurance for the FY 15 and 16 years. And that was basically learning, first of all, learning from the field what exists in the world, which is your standard literature review whenever you do a project. But what we ended up with is an algorithm for determining early in the life cycle, because having it on the last day of development isn't going to do you any good, but early, how complex is this going to be, and in a way that affects safety. So once we have that, then we can transition this kind of algorithm to a particular, oh, thank you, a particular need for, wow. For any other, well, it works okay, but any other usability, if you have a different quality attribute you're going to look at, if it's a safety one within the DoD or something, we can take this algorithm and adapt it to your concern and give you that kind of answers. So what we can do for the DoD is we've got this algorithm about determining the certifiability of safety given the architecture early in the program. Basically, what are the components and what kinds of errors can arrive at the different outputs to the components, as well as the fan out from there. And what we had as an alternative to determining complexity, because the first step in this was determining what do you mean by complexity, and how does it apply to avionics subsystems, for example. And we looked at the complexity of the design, for example, but we kind of got all wrapped around the axle trying to figure out how that relates to safety, as well as whether, for example, we would have any access to the data on a 747 or something like that. So we ended up picking the measure of complexity was how complex is the case that you have to make that the airplane is safe? Because that has a clear connection to complexity. And it also is tieable to the design or the architecture of the avionics that you can tell early by the following. Given that today's systems are complex, that they're safe, and they generally are considered to be safe, we made the assumption that the difference of something that's more complex and what would make that more unsafe is not changes in the components, but rather changes in the connections of the components to each other. Because when you have emergent failures, they always seem to be, oh, this thing started here and it went to that one and we didn't think about that. So in making the case that the system is safe, you're going to need to follow every single propagation of an error from one component to another and look at whether that's safe or not. And as the complexity of the system gets larger, that number of things you have to follow through and check for hazards or other reasons why it wouldn't be unsafe gets astronomically higher. At some point, you no longer have the resources, in the FAA's case, to review that safety case. So something like Boeing or Airbus would create the safety case, and the FAA has to have enough resources to actually review it. And that's where we were able to draw the line and say, at the point where you no longer have enough resources to track all the possible ways that this could fail, that's when you can no longer certify it as safe. There you go, Bob. He wanted me to give him a 25 words or less answer on that a while back, and I couldn't do it. So some of the lessons that, and we can do that, as I mentioned, for other quality attributes. The first reason this is valuable to the DoD is we have a suspicion today that some of the things that we're working with are too complex to be able to certify as safe or as anything else. And this kind of method can be used there too. It's possible to estimate safety from an early phase when you just have the design. Again, as I mentioned, if it takes until the safety case is complete before you can see how big it is, that's too late. Because you've already put all the decisions in and you built the thing, you've spent all your money, and there's no way to fix it if it doesn't work. So I have to give a lot of credit to Mike Conrad for coming up with a lot of the algorithms that were involved in those two steps. And the thing that's most relevant that I will tell you today, the 25 words to take away from Sarah's talk is, don't look at complexity as something that will be the same from somebody to somebody. You can do all the literature review you want, but if you're going to simplify complexity, work on that for a minute. If you're going to simplify complexity, in other words, talk about something in terms of what it isn't, it's not simple. If you're going to do that, you have to do it in a case-specific manner. So if we were going to come up with a proxy for complexity that related to safety, it had to be specifically related to safety in this case, and that's why we came up with a complexity of the safety case. That's not going to be transferable to something that's maybe not even, definitely not a safety case. We'll look at what it would be, but then in different kind of types of safety cases, it probably will be. But if you're looking at complexity for cost, it won't be usable for that. Well, I will say that, but then I talked to the FAA. Some of the aircraft manufacturers said, you know, we could use this to estimate our quality assurance effort. And I said, well, yeah, actually, you probably could. So there's a lot of applications that I probably shouldn't say you can't do. We would like to continue this research. We use some small system architecture drawings and small systems in creating this algorithm. We'd like to validate that it really works with a full system AADL design, for example. We'd also like to see what kinds of failure data we can use to validate this, because it turns out you can't validate anything with aircraft accident data. Do you know why? One, it's too rare, and there isn't enough. And second, once you've had one failure, you go and fix it. So you can't get statistics because you're not going to have that failure again. So we have to work with smaller components, and I mean, even going to incidents doesn't help me much. You have to work with smaller components and try to get your statistics that way. We'd also like to work better with the virtual integration body of knowledge, the AADL folks, and how they're working with the safety cases. And I have this kind of itch that I haven't been able to scratch yet. The question of precedence. If you've got a precedented system, namely you've been working with, say, a Boeing 737 this long for a certain period of time, and you know how it works, now you're going to stretch the fuselage. How do you take credit? How do you take credit for knowing this thing? And what's going to change when you stretch it? And that's, if you simplify that too much, it just becomes a question of regression testing. But there's something more to that. How do you take credit for the knowledge you have about something? And will that knowledge actually prevent an Ariane 5 disaster? Remember, in the Ariane 5, they used the Ariane 4 that they knew all about, but then it overflowed its buffers and everything blew up. How can you prevent that kind of thing? So I'd like to work on that in the future, and I haven't figured out a way to phrase it as actually doable research at this point. Some of the insights and observations we had is that complexity is not a thing, it's an adjective, it's a characteristic of something. I think that's the bottom. It's a characteristic of a system, an environment, or in some cases you can even talk about the complexity of a task. You can't talk about the complexity. Second, that there are causes and effects. And as we talked, Mike talked about the causal learning, if you change an effect of complexity, you're not going to change the complexity. You're just going to change how you can deal with it. You have to change a cause of complexity in order to change it. And now we could talk about how cause and effect get kind of muddled in complex systems if you want to talk about that. But certain things like the design, the number of stakeholders you have, the requirements, and technology change and things, these would be causes of complexity that if you tweak those, you could change the complexity of your system. Whereas things like the confusion you feel, the error that you might make, the difficulty you have designing, these kinds of things are effects. So keep in mind that you have to deal with the causes if you want to change things. A second column there, that we learned that if we want a complexity measurement, we can't do something that's only finished when the design is finished. We have to get earlier complexity proto measurement. And that measurement is useful when the complexity ties to something that makes a difference. Here, of course, it ties to safety because of this task, but before it ties to the effort it took to perform the certification task, the assurance effort. I also find from my doctoral work that complexity is best handled as a risk. So when you're working with something that's complex, if you can tie it to risks, that's probably the most beneficial way to address it. It's also problematic, as I mentioned before, to seek one measure that will capture complexity because it's so complex that you're going to need different measures for different purposes. We can use the algorithm to estimate quality assurance, as I mentioned, the FAA audience pointed out, and possibly even your testing strategy. You could use that as well. We'd have to work on that one. And that what we had done is count the number of potential error propagations. This is the short 25 words on what we did from one component to another within the initial architecture. How many ways can an error propagate from one component to another? And then each of those will be tied to how long it takes to prove that that path is safe, which of course will have some statistical average on that. We did lots and lots of assumptions in the papers, and I'll have the sites you can look at in a moment. And it is nice to reduce complexity, and it's important to certify it, but those things take time and energy. And in addition, some of the things you might put in to prevent a problem would also cause more complexity. So there's a kind of a fine line that you're dealing with there. Now, these are available online if you look at it. We have 5 previous reports, the literature, how do you define complexity, the candidate metrics of complexity. And again, that's not just software, that's system as well, which was new for us, really. And the impact of complexity on safety, estimating how complex is a safety argument, which ended up being the real thing, and then testing that. And then the final one, which does not include everything from the former, but rather just tells you what the output is the one in the top, the definition and measurement of complexity in the context of safety assurance report. I believe it's also up on the FAA site. I have not checked to verify that that's true, but they intended to put it up, change the front cover and put it up as their research. I'll take questions for a moment. Okay, we got one over here. Anybody else? Just get a microphone. Oh, oops. Oh. And we have another one over here.
You want to go first?
No, go ahead.
Okay, thank you.
Could we get a microphone over to this lady? Okay, go ahead.
In the beginning of your talk, you mentioned the objective is certifiability. That's what drove the research. Mm-hmm. Certifiability primarily depends upon V&V. So why wouldn't you not take quality attribute of certifiability to assurability to verifiability, and if to analyzability, understandability, and if you don't have these abilities satisfied, you don't proceed further. In other words, let the attributes drive the system architecture and the rest of the system engineering.
I think that that's an important question, an important idea. The FAA insisted that what we work with was their role in it and not in the aircraft manufacturer's role in the project. So we had to take this certain perspective when doing this research. I do think that the aircraft manufacturers need to do that, and the FAA would have the option, for example, of saying, show me your verifiability case before you even start. But I'm not sure that they're ready to take that step.
Second part of what you said was, how if I have something that's already certifiable or certified, and I know I want to extend it, how do I deal with it? Wouldn't you again apply a criterion of composability? The change plus the original must not create unanalyzed conditions.
Can we talk at the break? I'd love to talk to you at the break. And we got this one question.
Within a DoD, we have information assurance system called the Risk Management Framework. It's currently underway, and we're finding it to be a very difficult process to implement. And it is, in process-wise, although it's only 6 or so steps, it's not an easy step in itself. The way that we do information assurance certification, I know from a Navy perspective, is that we put a boundary around our system, and we certify and we mitigate the risk associated with that. But the issue is that our system is not a standalone system. It is integrated with other systems. I was just wondering, have Carnegie Mellon, SCI looked at potentially maybe extending this to address the integration aspects in terms of complex system and providing some insight into this information assurance certification, and maybe perhaps help the policy in terms of, rather than coming out with the policy, analyze it first so that it'd be easier to implement it at the deck plate.
Not that we have any little axes to grind or anything. Yeah, I would love to actually do that. I think that's really important. And if we could also talk maybe at the break, then we could get your contact information and continue that. And I'm going to point at Mike Conrad also, because he was so valuable on this project, and he can help guide me on answering your question as well.